All right, well, thank you everyone for attending my session. I manage the engineering team in Silicon Valley that works on artificial intelligence and multiple features for digital vehicle. We are actually the R&D arm of Daimler in North America. And what I would like to talk to you about today is how we're using intelligence and artificial intelligence in the user experience and creating a user experience for our user. This is the cabin or the view from inside the cabin of the concept IAA. This is the car that we have brought here for you. It's outside on the show floor area. And IAA stands for Intelligent Aerodynamic Automobile. And what's really intelligent about this car is that it transforms itself, it transforms its shape at certain speeds to actually have better aerodynamics. The car is out there, so please have a chance to look at it, and our colleagues can show it to you outside and explain it to you. But in general, what we are using and what we are working on, the topics we're working on and using artificial intelligence for in our office is basically, first one is the UX, user experience intelligence. Second one is the autonomous driving. And then third one is big data and analytics. And this is kind of like general categorization of all the topics we're working on. And what I would like to talk to you a little bit about today is the user experience intelligence. What we mean by user experience intelligence and what we can do with user experience intelligence is basically to make the experience inside the car as you step inside the car more intelligent and more customized. So the first thing we need to do is to identify the user, and we're using artificial intelligence to understand from different clues and different sensors who's actually the user that's inside the car. Second thing is that we do adaptive UI. UI is user interaction. So the idea there is that as you sit behind the wheel, we can automatically understand who you are, and based on that, change the screens, change the widgets, change the flow of the user interaction in order to be suitable for you. And as somebody else sits behind the wheel, they will get something else that's more customized toward them. Behavior modeling is the process of creating a model for how the user is interacting with the car. And why that is important? Because once we understand and once we have a model for how the user is interacting with the car, we can actually infer or predict what the user will do next, and can make the user experience much more intelligent by doing stuff for the user and proposing things that the user might want to do. User sensing is the area where we study how user is interacting in the 3D physical space inside the car, inside the cabin. Is the user looking up, looking down, looking right, looking left, waving with their hands, trying to do something, trying to reach the light, things like that. And we're using models inside the car to predict and understand what the user is actually doing in that 3D physical space. And then finally, if we have intelligence that will tell us what the user wants to do, and if we're confident enough, we can automate that action for the user. If I know that the user is going to work every Monday at 7 o'clock, maybe I can just show the traffic to work. Things like that. If I have enough confidence based on all this intelligence I put in the car, I can automate things for the user without the user actually requesting that. I would like to focus a little bit on the behavior modeling. And I don't want to talk about a concept or a prototype or a research. I want to talk about a product. And today I choose a product to discuss with you and dive deeper into one of these products. And the case study I brought with me and the product I would like to talk about is our latest S-Class or newest S-Class Cabriolet. This is a car that we showed at Frankfurt Auto Show a few weeks ago. And in this car, we put our latest machine learning algorithm. What it does, actually, and that's what I would like to share with you today, is that every time you sit behind the wheel, the car will know where you're going. So this is basically what we put in there. Sounds like a simple and easy thing, but it's very critical and important. And the way we enable that is, first step is that you first enable this feature. And that's very important because one of the things about AI is that you need to build that trust between the machine and the user, and you need to give the user full control over the experience. The first thing you want to highlight there and you want to show there is that the user control that, can enable it or disable it. So that's the first thing you do when you get the car for the first time. So we call it intelligent destination suggestions, and you get that, and you enable that feature when you get the car. And what happens after that is every time you try to use your navigation, we give you predicted destinations we learn and believe that you will be actually going to. Imagine, like some of you actually drove here, some of the brave ones actually drove here, and those people who drove here probably park it somewhere nearby, and by 5, 6, 7 p.m. will go back to the parking lot to pick up the car. What you will see when you go to your navigation, no matter which car you have, what you will see when you go to your navigation in the car that you've driven here is that the first thing that shows in the previous destination is the destination, the address to this location, which doesn't make any sense. And that's exactly the problem. Everyone among us will actually know that you will not need to come here again if you are here. But the cars so far do not know that, and the car will just show you the destination, the previous destination, the destination that you just went to. If it's Sunday and you go to the beach with your kids and you go to ice cream shop and you go to a restaurant nearby the beach and have lunch there or dinner, and then Monday morning you get to your car and you go to your destination list, and the first 5, 6 destinations are all about the beach and what you did on Sunday night and Sunday morning on the beach, which doesn't make any sense. So what we are doing here is that we're trying to make that experience more intelligent. By understanding the user behavior, by understanding the context around the experience, and with that we can actually know where you're going or where you want to go without you inputting a destination in the system. So if it's Monday morning, 7 o'clock, and you are at home, based on your behavior in all the previous Mondays, you're most likely going to work, and you most likely want to check the traffic. And these are the things that you should see in this destination list and make the experience much easier for you. So this is a feature, and this is a product that you will be able to use in our cars. And how it was developed, what happened behind the scene to make this actually possible, is that we wrote the algorithm, we wrote the machine learning algorithm, and the software that enables that in our office in Silicon Valley, so it's all in-house development. And we actually integrated that inside the rest of the code that runs our head unit, which is the computer on the dash. We validated that model for 3 years. So while you will see that model in the cars that are released this year, it's actually been going on for 3 years. The model we developed, we tested for 3 years in order to make sure that it's solid enough and it actually will help the user instead of irritating the user. About 40,000 trips, that's what we did. So we had multiple cars, multiple people, multiple locations, and we basically drove. We drove to all these different areas and locations, and we experiment with what it means to have a trip. Is it like when you start at your home and you go to pick up the kids from school, if you stop on a traffic light, is that a stop or is that a temporary stop? If you stop to take gas, to pick up gas or fill, the car with gas? Is that stop? Is that the end of the trip, or is there something in the middle? And the algorithm has to account for all of these use cases, has to understand the beginning of the trip, the end of the trip, and has to understand the context around this whole experience. That's what we did by driving around 40,000 trips. The context that we added there basically comes from the vehicle sensors. And we're lucky enough that there are hundreds and hundreds of sensors in the car, so that the trick is not to find new sensors. The trick is to find the right ones, the ones that will actually impact the experience and will make it possible for us to have the best prediction for the destination you're going to. What we found, of course, is that your location is very important, where you are. That is one of the basic things. The time is very important. What time of the day, which day of the week, which months of the year, all of these things will actually impact a lot the experience that you will have and will decide where you're going to go if you are behind the wheel. We actually, after that, started to create the model. We selected the model. We started to create the model. And it took us about 18,000 NVIDIA hours on the Titan X GPU. And I would like to dive a little bit deeper into this, since we are at the NVIDIA conference. I would like to dive a little bit deeper into this to actually explain what actually took us these 18,000 hours. So a little bit behind the scene there, what we do when we have an AI project, and we have multiple projects like that, what we do in general, and what all of you probably are doing, nothing new here, is that you start with data gathering. You make sure that you have enough data because you cannot create a model or you cannot optimize your model if you don't have enough data. So data gathering is the first step. You identify your objectives. What are you trying to do? What is your KPI? What is the final experience that you want to provide from that model? That's very important very early on in the process. You start preparing your data. You clean up your data, more or less. It's a very important process. There are duplicates in the data. There's data that doesn't make sense. There's data that will actually make the model very difficult to diverge. So you clean up your data. You prepare your data. And then you start the model selection process, and that's an iterative process based on, well, on the data that you have and how you cleaned it. And then after that, you start optimizing and, well, evaluate the model, optimizing the model. And again, that step will make you go back to your objective and say, is these models that I have now actually gonna give me or make me reach the objectives that I defined for myself or defined to me by my executives and my customers? And then you deploy the model. In our case, we deploy the model in the car. So after we test and define the parameters and validate the model, we actually have to take that model that we create probably in Python or some other language and shift it to put it inside the car in a different language, in a different environment, on a different operating system, a different hardware. So that's a big step, and we have to make sure that this will also work fine and the model will work, we call it on the edge, because we put it in the car and it's basically out there in the hands of customers. So these are the normal steps. And if we look a little bit about, or look a little bit deeper into the model selection, model evaluation, we can see the issue that we are dealing with and the challenges that we have. The model we selected for this simple use case of predicting where you're going, we had 35 hyperparameters for that model. And if you think about this, there are 35 different possibilities for those parameters, for 35 different parameters, and for each one of those, there are multiple possibilities. And you need to evaluate your model based on this set of parameters. And if you just assume that each of those parameters can take two values, which is not the case, obviously, but just for assumption here, for assumption's sake, to understand the complexity of it, if you assume each of those parameters will only take two values, then you will end up with about 34 billion combination of these parameters. 34 billion combinations that you need to evaluate. Now, each evaluation, each time we need to run the model to evaluate is taking about half an hour. on that Titan device, Titan computer that we have. So obviously, we cannot test this. There is no way we can test all possible combination. If we only take just 10%, even 10%, like only 3 billion of these combination, you will end up with about 200,000 years to evaluate this. So there is no way you can do that, obviously. So for such a model, there is no way you can evaluate even 10% of all possible parameters, assuming that each parameter takes 2 values. So what do? We have to look for different ways to select those parameters. So we look at different ways. A grid layout is one of the famous ways of doing this. And what you do, this is just an example in the 2D space. Of course, we have multiple dimensions, but in just 2D space, you select parameters in the 2D space. You provide some values, and you evaluate those. Usually, if you can see that green, the green function and the yellow function on the sides, this is the performance that you get from those parameters. In general, if you use the grid, you could miss the optimum case, as you can see here in that very simplistic example. So what you do is that you do random layout. Random layout is that in your space, in your parameter space, you select randomly some parameters, and that will hopefully will give you the optimum parameter, or give you the optimum performance for a certain set of parameters. It's actually a very good method, and it's usually straightforward to be used, and it can be parallelized because these are random parameters, and each set is independent from the other set, so you can actually parallelize this and get the performance in real time of multiple different sets. So that makes it very attractive for us to use. But it's still, it works better if you actually can evaluate and get the performance of your model a little bit faster than half an hour. In our case, every time we run the model, it takes us half an hour. So the random layout actually didn't work in our case. So we used Bayesian optimization. And what we do in Bayesian optimization is we create or we find a secondary learner that learns to predict the performance of our parameters. So that is our goal here, is instead of keep trying, we try to create this or find a secondary learner that can predict for us how different set of parameters will perform. And we define acquisition function based on that secondary learner, and that acquisition function will help us to find the areas in the parameter space where we should sample and pick up a new set of parameters to evaluate. So what you see here in that graph is a representation of this. And I'm gonna, in the next slide, I'm gonna explain it a little bit more. But what we found from this is that it's very effective because we only spend time in the areas, in the parameter space, in the areas where we expect maximum outcome. Basically, better performance for these parameters. And it still could be parallelized, which is an advantage in this case because you can run multiple threads at the same time. Let's look a little bit deeper into this. So the first step here is that you choose parameters. So the graph on the right here is basically t equal 2 is that you have, this is the second parameter set you're testing. T equal 3 is the third parameter set that you're testing. So you're basically starting with one parameter set, and then from there you try to pick up the best location in the parameter space for the second parameter set, and so on. So what we do here is you can see that we choose parameters at the maximum of the acquisition function. So this acquisition function is the green function at the bottom, and we go the maximum point of that function and pick up that point in the parameter space to select that set of parameters to evaluate. And by evaluating that set of parameters, which is basically meaning that I use that set of parameters to run the model, it's a slow process, but it helps me to evaluate candidate parameters. So it gives me actually the dotted line. And from there, I can go very quickly and I update the secondary model, which basically is a solid line, it's uncertainty around it, this blue area around it. It enables me to do that, and then I iterate on that process. So I go from there, again, very fast to, again, pick up the parameter set at the maximum of the acquisition function. That process keeps going, and it helps me, as I keep doing this, to define this secondary learner and tell me exactly where in the space, in the parameter space, I can pick up the right set of parameters. So quickly, what's next? Knowledge. So this is how we did that. This is already a product in the car. Where are we going next? Well, knowledge is intelligence. We feel that. And as human, we become more intelligent by gaining more knowledge. So we're bringing more knowledge to our algorithm. We're looking at, for example, the gesture and gaze as different input to our model. We're looking at how we add more environmental sensors. We found that environmental sensors are very basic for our algorithm. The weather outside, for example, will decide where you go. You're not going to go play tennis if it's raining, even if that's your habit every Friday night. Adding the cloud information that we have about ourselves could help the model very, very much to identify what you're going to do next. And of course, if we have access to the social space, that will add to the preference or the knowledge about the preference of certain user. At the end, we are defining a digital companion. We look at the car as a digital companion. We want the car to be your digital companion. And it's a centralized experience. It's a centralized intelligence that we put in the car that perceives the world just like anybody else. That's the first step in it. So that intelligence, that's AI in the car, has to perceive the world just like all of us. And then it has to be able to interact with the user inside the car in a way that any human would interact with the user. And it has to be able to build the trust between itself and the user, so the user can depend on it, because at one point it will help the user, will automate things for the user. That's all. Thank you very much.
Thank you, Kal.